to analyze independencies in the graph, in the network. So one thing that we're trying to do, I just thought it's useful to highlight this point. A basenet in general, there is a graph, as you all know, there's a directed acyclic graph, and there are these tables, these conditional probability tables. Now, what we are trying to do when we analyze these independencies or dependencies in the network is that, we are just looking at the network structure, basically the graph structure. We are ignoring the tables, and for a given graph structure, is there a general statement that we can make about the independencies that exist, okay, among these random variables? Okay, so if you just take a graph that encodes a family of distributions, okay, so all of these family of distributions satisfy this way of writing the joint, okay, right, about the dependencies that exist. Just if you know the parents, then you don't need other information. So that kind of a dependency exists for any you can put in any tables here. Okay, so if all any kind of tables that you put in here, all conditional probability tables will satisfy this kind of a joint distribution structure. Okay, and now what we are saying in when we analyzed these cases, right, we saw these three cases, is just looking at the network structure alone, right? Can we make a statement about independencies in the network? Okay, so here we are not specifically tying it down to any particular conditional probability table. So that is something, like, if you noticed, all our proofs, it was very general. We didn't use any specific numbers here. Okay, so that's something I just wanted to highlight and what we're trying to do. And our approach was, we constructed three cases. So it's basically networks, all kind of networks that you can have with three random variables. And then we tried to analyze what kind of dependencies can exist. So the causal chain was this kind of a chain structure. And you're basically interested in seeing whether some information about X can reach Z. Okay. And what we said is, as such, yes, information can flow from X to Z. But if you know Y, then there is X and Z, you can say that they are conditionally independent if you know the value of Y. If you are given the value of Y, it's like Y blocks X from Z. Okay, so you have this independency, and we proved this. And all our proofs made use of the structure of the network in doing it. And so this was one structure, the causal chain. The other example, case 2, that we saw was this common cause, where you have a Y which leads to X and Z. So this is the structure. And here also the same kind of relation holds. So if you don't know Y, then there is some kind of there can be dependencies between X and Z. But if you know the value of Y, then X and Z are guaranteed to be independent given the value of Y. So this statement that we are making here, this has, it's true, whatever tables, there are different conditional probability tables that you can have here. The different numbers that you can have here. For any numbers that you plug in here, this relation is guaranteed to hold for this network. Okay, so that's what this means. And when you say that, X and Z, as such, they are not, they're not independent, or, you cannot say anything. So it means that, it is possible to plug in some numbers here such that X and Z are dependent as such. But when you put in the value of Y, if you know the value of Y, then definitely X and Z are going to be independent. Okay, so that's the meaning of all this analysis. Okay, and so this was case 2, and so we did this, and then we went to case 3, which was a slightly different case. So this was the common effect case. So where you have X and Z, two random variables, which together are responsible for Y in some sense. Okay, so here what we had, the reverse sort of relationship, right? So once you observe Y, there's something that you know about X, and that will tell you, something about Z as well. So if you know Y, then X and Z can become dependent. Okay, but if you don't know Y, then X and Z are independent. Okay, so that's sort of a flipped case. I mean, it's exactly opposite to cases 1 and 2. And so we proved this fact. And so what we had to prove was probability of x and z is this product p of x times p of z. And this is true for every value of x. So this, what you have to show when you show this kind of an independence, is for every value of x and z that you take, this relation has to be true. Okay, so that's what you want to prove. And we did this yesterday in class. So I also wanted to just tell some points about some of the other methods. So I think Rishabh and Advait had some alternate approaches. So one of the approaches I just want to just elaborate a little more. So one thing that was said was, you have this kind of a joint, right? And from this, you can take out the value of p of x times p of z, right? And so it's basically like trying to rearrange this equation, right, the joint equation. So let me just write that once again. So there's something we wrote here, but let me just write it here for the sake of clarity. Okay. So the approach suggested was, you have this joint p of x y z. So this is equal to p of x p of z times p of y given x z. Okay, that is from the network. Okay, so because of this network, I just copied down this equation there. So this is the expression. Now you take out this part alone. So p of x z is p of x y z by p of y given x z. So here, what is going on here is you're introducing a new value of y here. Okay, so this is where you have to be a bit careful, because this expression, this is true for every xyz pair. I mean, every xyz triple. So for all values of small x, small y, and small z, this is true. Okay, that's what this statement means. So okay, but one thing, when you write this kind of, when you rearrange these terms, you have to ensure that this term p of y given x z, for this particular y and this particular combination of values, this should not become zero, right? So otherwise you cannot do this kind of a rearrangement. Okay, so that is something to you have to watch out for. But otherwise, the if you're guaranteed that this holds, you take any specific value of y and you rearrange this, and then you use chain rule here. Or maybe you can write something like this: p of xy given, I mean, times p of z given x equal to x, y equal to y, right? So this is something that you can do. And okay, sorry, did I think I had to write it the other way, right? So p of x and z times p of y equals y given x equal to x and z equal to z, times p, I mean, divided by p of y by. Okay, so these two you can cancel provided this is a non-zero probability, and then you have it. So I think the left-hand side was again p of x times p of z, right? P of x times p of z. Okay, so yeah, the idea is fine. There's nothing wrong with it, but just you have to be careful when you insert a new y here. You have to be careful that things don't become zero and all that. Whereas what happens is, now the other approach which I mentioned was using the total law, where you can sum up all the values of y. So here it's okay. There is this statement is always true. For all values of y, you can marginalize out, and then you can you can move the sum inside, and things in this summation becomes one, and you get the required equality. Okay, so this is something that I just wanted to specifically highlight. So what we said is, x and z are as such independent, and if you know why, then you can't say they can become dependent. Okay, so how do you prove that they can become dependent? If you know why, then x and z can be dependent. So what I said is, you can construct examples. So I just thought it's worthwhile to give you one example And you can try out, you can work out the values yourself. But what does it mean to construct an example? I just wanted to tell you. So let's just take this same, this application where grass is wet, rain, and sprinklers on. So this is the example we saw. So I'll just use some other representations here. So there's one random variable saying the grass is wet. So this is wet grass. And the reasons are the sprinkler being on or rain. Okay, so this is rain and this is the condition of the sprinkler. Okay, so all these are Bernoulli random variables. They take values 0 or 1. So let's take one example where probability R is 1. So what I'm writing is what are the conditional probability tables that you can that will be given with this network. So one is probability R equals 1, so probability that it rains. So let us say that is something like zero point 0.9. Okay, and probability that the sprinkler is on, let us say this value is 0.7. Okay, and so what is probability R equal to 0? Probability it doesn't rain.
0.1.
0.1, right? Yes, and probability S is 0 is
0.3.
0.3. Okay, so now I'm going to construct the other distribution. So what's the probability that the grass is wet given that it rains and the sprinkler is on? So this value, I'm putting it as 0.9. Okay. So what other value can I immediately say from this? There are 8 configurations, right, for W, R, and S. So I have to list out all of that. So some other value I can say from this.
W equals to 0, given R and S equals to 1.
Exactly. Yes, exactly. So probability W equal to 0, given R equal to 1, S is equal to 1 is 0.1. And let me take the probability of W equal to 1 given it doesn't rain and the sprinkler being on. So let me call this, let me say this is 0.7. And similarly, you have the other probability. Now, probability of W equal to 1 given R equal to 0, S equal to 0. So this value, let me take it as a very small probability, 0.1. And probability of W equal to 1 given what's the other, what else is left?
R is equal to
R
1.
equals to 1 and S equals to 0.
Yeah, R equal to 1, S is 0. So this value, let me take it as maybe a 0.8. Okay, so these are some example CPTs, the conditional probability tables. So of course, once you have these, immediately you get these other values. Okay, so I'm just not writing it, but yeah, you will need to use it to check these conditions. So what you have to check now is whether it is true that probability of R equal to 1, S is equal to 1, given W equal to 1. Is this equal to the probability of R equal to 1 given W equal to 1 times probability S equal to 1 given W equal to 1? Okay, so this is what you have to check, and you have to do this for every configuration. So there are 8 such possibilities, right? So you have to try this for S is equal to 0 given W equal to 1, whether that's equal to this product, probability R equal to 1 times probability S is equal to 0 given W equal to 1, and so on. So all these 8 possibilities you have to check. And if at least one of them doesn't hold, if at least one of these equalities doesn't hold, then you can say that, yeah, see, here's an example where, you don't have that as R and S are, R and S can be dependent given W is 1. So if they were independent, if they were conditionally independent of W, then what you would have is, all these 8 equalities would be true. Okay, so that's what it means to check, to give an example or to construct an example where some independencies don't hold. Okay, so this is something you have to verify, and each of these you can verify from the network. So let's just do one of them. So maybe let's take probability R equal to 1, S is equal to 1 given W equal to 1. Let's try to evaluate this probability. So how do we do that? The network is this. So maybe let me just copy it down. How will I estimate this probability given this network? There's a conditional probability. So what is the expression for the conditional probability? How do you evaluate this?
P of R equal to 1, like the joint probability upon P of W equal to 1.
Yeah. Okay. So this is what you need to do. And what about this joint? You have a way to write it from the base net. So how do we write that? What's the value? Let's just do one or two values and then
P of
we'll move.
S is equal to 1
P of S is equal to 1.
into P of R is equal to 1
Okay.
into P of W is equal to 1 given S is equal to 1 and R is equal to 1.
Sure. That's perfect. So probability S is equal to 1. We've written this as 0.7. So that's the number. So 0.7 times what's the probability at R equal to 1?
0.9.
0.9, right? 0.9. And what about this probability? W equal to 1?
0.9.
0.9. Okay. Yeah, so that's how you will compute this. Now, probability of W equal to 1. So how do you evaluate this, right? So what you only have is these numbers, okay, all these probabilities. So one way is to sum up over all possible values of R and S. So this would be probability R equal to 0, S equal to 0, W equal to 1 plus probability R equal to 0, S equal to 1, W equal to 1 plus probability, what else is left?
R is equal to 1, S is equal to 0.
Yes, and
All zeros. R is equal to 0 and S is equal to 0.
so R equal to 1, right? So R
All
equal to
one.
0, S is
Sorry,
0
sorry.
is
R is
3.
equal to 1 and S is equal to 1.
Yeah, right. So you have these four joint probabilities. This again you estimate in the same manner. I mean, you compute it in the same manner like we did, plugging in the necessary values, and you do this. So you're able to compute this number. Now same thing you do for probability R equal to 1 given W equal to 1. Okay, so here again you will have to get this joint divided by probability of W equal to 1. Okay, and this number, the numerator again try to marginalize over Z. I mean, sorry, over S, not Z, S. Okay, so you take S equal to 0, S equal to 1. So there'll be two summations here. Okay, and so I'm just writing it once so that you know how to go about in case there's some confusions. Okay. Okay, so you try to, I mean, you compute these numbers, and again, you do the same thing for probability of S equal to 1 given W equal to 1. You'll get a number, you multiply the two, and you see whether, that matches with this probability. Okay, and similarly, like this, you have to do it for all the 8 cases, and, if sometimes it could happen that for some of the cases, you have these equalities actually hold, but so you in that case you have to proceed and check every case to ensure that some whether some case there's been violation. Okay, so yeah, what I will leave it to you is just try out these numbers, see what you get, and try to see whether independence really holds here given W or not. Okay. Yeah. So yeah, this is a homework for you to complete these computations. So where we left off last class is we talked of these triples. So why did we talk of these three cases? So our objective is ultimately to analyze even larger networks and to say something about the dependencies that exist in the network, irrespective of the tables that are given. Okay. So in that context, what we saw is this notion of triples. So any group of three random variables that we refer to as a triple. And we defined these sort of active and inactive triples. So what it meant is you want to see whether there's some flow of information from one random variable to the other in the network. So if you have this causal chain here, if you don't observe y, then what we said is x and z can be dependent. So there can be a flow of information from x to z. So in that sense, this is an active triple. But the moment you see y, so that's marked, I mean, the way we represent that, y is observed or there is an evidence y is by shading this node y. Okay. So the moment you see y, then x and z become conditionally independent. So this was case one. Okay, so that was case one that we analyzed. So in that sense, X and Z are said to be blocked. Okay, or this triple is actually called an inactive triple. Okay, because what you see at X doesn't come to Z because there is Y in between and Y is observed. Okay. Now, similarly, the other cases you had case two where this kind of a common cause. So this was case two, and so x and z as such there can be a flow of information, but the moment you observe y, what you know about x doesn't impact z, so there's no influence in some sense, so there's no flow, and so this is an inactive triple. Now, in case three was what we did today as well. So this was x and z leading to y. So here, if you observe y, then there is something about x that helps in z, in your knowledge of z. So in that sense, x and z, I mean, this triple is active if you know y. Y, then x and z are inactive. I mean, this triple is inactive, and x and z are you can say that they are blocked out from each other. Okay. An important thing here is there is also a further case. Okay, so this is an extension of case three in some sense. This one. So where it could be that x, y, and z, all these, none of these are observed, but you have some node somewhere deep in the network, and that is observed. Okay, so you have some kind of a chain here from y to y dash, and y dash is observed. So even then, what is happening intuitively is when you see y dash, then there's something you can say about y, right? And so once you can say something about y, then there's a flow of information from x to z. Okay, so even this is an active. So xyz is an active triple even in this case. Okay. Whereas now, if you look at all paths going out from y, and none of these nodes, which emanate from y, if all of them are not observed, then you have that there is x and z are again independent. Okay, or it's an inactive triple. Okay, xyz is now an inactive triple in this case. Okay, so these are the cases, and that will form the building blocks for our algorithm. Okay, so let me just tell you how what you should do. So before that, we'll just see, like we saw inactive and active triples. Now we'll also see what it means for a path to be active or inactive. So let us say so do you know what is a path? You've learned discrete structures, I guess. So have you seen paths in a graph? Yes, no, not sure.
A node is not repeated.
Yeah. Okay, so it's basically a sequence of nodes, right? So path is just the sequence of nodes. Okay, and here we are considering the case where you don't have cycles. So that's what Advait said, that there's no repetition of nodes. So okay, so sequence of nodes without repetitions. So to be very specific, a path can refer to cycles, but here we are looking at these sort of simple paths. So where you don't have cycles or where there are no repetitions, without any repetitions. So when do we say a path is active? Now we have what we saw as triples. So groups of three nodes, we said what it means to be active or inactive. Now a path is just composed of several such nodes, right? So it's basically a sequence of such nodes. Okay, and we say that a path is active if every triple is active. So if every triple in the path is active. So if every triple is active. So let's just say this. So suppose this is a path. So A, B, C, D, E, F. Okay. So then here, what are all the triples? The triples here are A, B, C, B, C, D, C, D, E, and D, E, F. Okay. So if all these are active, then the path is active. Okay, so even if one of them is inactive, so it means that that triple is blocking. So suppose ABC is active. So if ABC is active and just BCD alone is inactive, and all the others ABC, CDE, and DEF, if all these are active triples but only BCD is inactive, then immediately this is an inactive path. So this path ABCDE becomes ABCDEF. So this becomes an inactive path. Okay. I hope you get the idea. So what it just means is, once a triple becomes inactive, then it is as if it's blocking out everything else, right? So basically, when you say a path is active, it's, in this case, you want to see whether an information actually flows from A to F along this path. Okay, and the moment you have an inactive triple somewhere, then it's gonna prevent the flow of information, and so that path becomes inactive. Okay, but whereas if every triple is active, then that is the only time when information flows. Okay, so is this notion clear of active and inactive paths? Any questions on this? Yes, no? Is there some confusion? Maybe we can do some examples
No,
for
no.
it. It's clear? Okay. All right. So yeah, so we will use this notion of active and inactive paths in the algorithm. So what I'm going to tell you now is the D-separation algorithm. So here what you want to do is, the question is, the input is two random variables. So what you want to see is, xi and xj. So the question is, are they conditionally independent? Right, given some evidence z1 to zk. So let me call these evidences as z1 to zk. So this is what you want to see. So this is the query that you're going to get, and you want to conclude from the network whether this is going to be true. Okay, so the method to do this is, first thing is you look at all the undirected paths. Okay, so in the network you look at all undirected paths, so ignore the direction of the arcs, and you look at all the undirected paths from xi to xj. Okay. Okay, and then what you see that, then you look at each path whether it's active or inactive. So if all paths are inactive, if all paths are inactive, so now when you look at the active or inactive path, here you have to look at the directions. So here with the directions, if all the paths are inactive, then that means there is no way that information from xi comes to xj. So then we have that xi is conditionally independent of xj given all these evidence. Okay. And even if one path is active, if at least one path is active, um, if at least one path is active, again it's the same with directions. Okay, considering the directions, then we say that xi is not conditionally independent. So it's not conditionally independent of xj given z1 to zk in general. So this is the algorithm. So maybe we'll just see some examples. Okay. So first, let's just take a very simple case where you have two nodes. Okay. So there's A and B. Now the question is A independent of B? So here there is the evidence, there is no evidence. So these are Z1 to Zk, these are the evidence. So these are the evidence random variables. Okay, so here when you just say A is independent of B, that means the evidence is null set. So there's no evidence. So what do we know here? Can information from A reach B if this is the network that's given?
There are no paths from A to B.
No paths from A to B. So there's no possible way of the information being propagated. So this statement is true. So here the answer is yes. So A is independent of B. So that we can say from just looking at this network. Okay. So let's look at some more examples now. So maybe let me just, so I've just written down some examples. So maybe it's useful to discuss those. Okay, so this is actually the rain traffic, that network. So there's rain which causes traffic, and it can also be caused by a match or a ball game. So this is the example from Russell Norvig and also the Berkeley course. Okay, so there's this network, and there's also one more random variable here. So this is like T dash. Okay, so T dash is actually, you can think of it as a noisy measurement. So some way you have to measure the traffic. So this is the actual value, whether traffic there is large traffic or not. And T dash is a noisy measurement. Okay, maybe they have some sensors, and it measures the traffic. So T dash is a noisy measurement of T. Okay, so that's the intuition of this network, and so this is actually you know the probability that this is the random variable which says that whether a ball game happens or not. Okay, so this is the network. Now I want to see whether R is conditionally independent of T dash. Okay, so this is R and this is T dash. I want to see whether R is conditionally independent of T dash. I don't have any evidence. Okay, so how do I do this? So first thing is to list all the paths from R to T dash. So what are the paths?
RTD dash.
RTT dash, right? Okay, so now what you do is, okay, so this is just, it has three nodes. There's just a single path. Okay, and so is this an active triple or is this an inactive triple? Right, so here
Active.
there's, yeah, so this is active, right? So the underlying structure is just the causal chain RTT dash, and we have that there's no evidence, so it's case one, so it is an active triple. Okay, so this is active triple, and the path itself is just the triple, so this path is active. So this we cannot guarantee. Okay, so so you cannot say that. I mean, so generally R and T dash are not independent in general. Okay, so not independent in general. Okay, so now what if I observe T? So this is one case. Now suppose I observe T dash. So T is my evidence. So what happens here? What are the paths now? Paths from R to T
Same.
dash. It's the same, right? So the path, this is one path which is R T T dash. Is this active or it's inactive?
Inactive.
This is inactive, right? So this is inactive because T is observed. So once you observe T, R and T dash get separated out. So this is inactive. So this conditional independence is true. Okay. So so there's no way that information from R reaches T dash if you know T. Okay. So this independence is true. Okay. So now let's see what happens about R and B. So is R conditionally independent of B? So what are the paths here?
There won't be any path because we are considering directions.
Yeah, so here is where there's a slight difference. So when you look at the paths, you have to look at all the undirected paths. So ignore the directions. So when you ignore the directions, you have RTB. Okay, so there is one path. Now, in order to check whether this path is active or inactive, in that case, you take the directions into account. Okay, so the first part where you list down the paths, you ignore the directions completely. Okay, so now what this means is RTB is one path, but the triple is like this. Okay, so this is actually the path. It's with the undirected path. Yes, there is a path, and if you look at the directions, this is the path. Okay, and now there is no evidence, right? So what happens here? So is this an active triple or it's an inactive triple?
Inactive.
Inactive.
So this is an inactive triple, right? You don't know anything about T, and you also don't know T dash, or you don't know anything about what happens below T. So this is an inactive triple, right? So yeah, so there's no way information flows from R to B. So this independence is true. Okay. So what happens if I know T dash? What is the path again?
RTB.
Yeah, so the path is just RTB. And is it now active or inactive? It's again R, B, and T. Okay, you have this. And there is a T dash here, which is observed. So what happens here is RTB an active or inactive triple?
Ma'am, but T dash is not in our path, right?
Yeah. So T dash is not in your path, but still the fact that you have an evidence tells you something about T. Okay, so it's as if T is also observed. So that's the difference in this case. So even though we are looking at triples, you have to consider the presence of evidence nodes later down in the network. Okay? So even though it's T dash which is observed, this triple RTB is still active. Okay, so that's a distinction here. The intuitive idea is just this. Though this is a triple, now because T dash is observed, it means that there's something you know about T. You can infer something about T. And so these two R and B, they can be dependent. Okay. Advait, is it clear?
Yes, ma'am. But let's say we like wrote the algorithm, like we wrote a code for this.
Mhm.
So do we will we have to like for each triple check the graph till we reach a end node to see if one of the bottom nodes was is given as evidence?
Yes, you have to do that. You have to look at all the, all the parts, I mean, all the nodes which come out from T. And yeah, you have to ensure that none of these are observed. If you want to conclude that this is an inactive triple, it is true only if none of these nodes in this network are, if they are not observed. So yes, you have to go through all of them.
Okay.
So it's basically this case, right? So here, so everything below y has to be unobserved for this XYZ triple to be inactive. Okay. Yeah. So I hope this is clear. Are there any questions? Are there any confusions on this part, on these examples? We will work out some more, but I just want to just get a sense of whether this is clear so far. Can you just type in the chat box? Okay. Okay. Great. Okay, so maybe we'll do some more examples. I'll just see whether something I had to tell in this part. We did R given P or yeah. So even the same thing holds for if you know T, right? So this R given, I mean R and B, whether they are conditionally independent given T, right? So okay, so the conclusion here is these are active. This is an active triple. So here we cannot guarantee conditional independence. So conditional independence doesn't hold in general. Now the same thing happens even when you observe T, right? So it's exactly case three, and so RTB becomes an active triple. Okay, and so we cannot guarantee this. Okay, so yeah. All right, so let's take a maybe slightly larger example. So let's do this one. Okay, so we have something like this. So this is like a modified example of, I mean, it's some more random variables added to this rain traffic network. So this is like low pressure. Low pressure causes rain, and rain and the ball game together decide on traffic, and there is a T dash. Okay, and there's also this thing about D. Okay, so this is a random variable which says that there is a dripping roof. Okay. Okay, so this is rain and this is ball game. Okay, so just two more random variables added, L and D are added. So here, let's see. So what about L and T dash? Are they independent? Yeah, if you know, say, if you know R. So what are the paths here? So maybe I'll ask somebody to answer. Maybe Kushbu, can you try this? Kushbu, you're there? Am I audible? I hope I'm not disconnected.
Yes, ma'am, you are audible.
Okay, so Kushbu is not answering. So I don't know what's up, whether she's there or she got disconnected. Uh, okay. Kushbu, are you here?
Yes, ma'am, I'm here.
Okay, okay. So can you try this one? So we're trying to analyze this network and this question on dependencies, whether L and T dash, whether they are conditionally independent given R. Right. So can you just tell me what are the paths from L to T dash?
L R T T dash.
So L R T T dash. So this is the path, and this is the only path, right?
Yes, ma'am.
Okay. So now what you do is, what are the triples here?
LRT
Yes.
RT T dash.
R T T dash. Yes. Okay. That's it, right? So just two
Yeah.
triples,
Yeah.
right? Yeah. So remember that when you write triples, you look at what all connections are there. So for example, LTT dash is not a triple, okay, because there's no direct connection between L and T. Okay. Fine. So what about LRT? Is this an active triple? So rain is observed. So it comes like this. So rain is actually observed.
Inactive.
So this is inactive, right? Yeah, it's because
Yeah.
you know R, then information from L doesn't go to T. Yes. So this is inactive. So immediately now you can say that this path is an inactive path because
Yes.
you have a block. Okay. But let's just do this. What about RT T dash? Is this an active triple or it's an inactive triple?
I think it's an active triple.
So RT T dash, okay, so it's actually active. So it would have been inactive if you observed T, right? So now what you're observing is just R, and T is not observed. So once, if you have R, there's something you can tell about T dash also. Okay, so this case actually becomes an active triple. Okay, is this clear?
Yes, ma'am.
Yes. Okay. I'm sure. I mean, these are some of the confusions that arise when you try to solve this. So I thought it's good to just do some questions like this in class. Okay. So these two triples are, we have this information that LRT is inactive, RT T dash is active. So immediately this path becomes inactive. Okay. So this answer to this question is L conditionally independent of T dash given R. So all paths are inactive. There's just one path and it's inactive. So the answer here is yes. Okay. Fine. So now let's do something else. Okay. Let's do L, whether L is independent of B. Okay. So there's no evidence here. Is L independent of B? So maybe somebody else can answer. I don't know who wants to try. Maybe Deep Gupta.
Yes, ma'am.
Yeah. Would you like to try this? So L and B is what we are seeing. So what are the paths first?
From L to B.
Yes.
Uh, till T it is there, but ma'am,
Yeah.
okay,
So yeah. So again, you look at when you list the paths, you look at all the you ignore the directions and you list the paths. Okay. Only when you analyze the triples do you look at the directions.
okay.
Okay. So yeah. So what are the paths here?
From L to B, it will be LRTB.
LRTB. Okay. So yeah. So what are the triples now?
LRT and R. We are observing which one?
So there's no evidence here. You're not observing anything. So let me just remove this. Yeah. So there's no observation here.
Okay. LRT and RTB.
Okay. So is LRT an active triple?
LRT is an active triple.
LRT is active or inactive? What did you say?
LRT is active.
LRT is active, right? So nothing is observed. So information from L goes to T. What about RTB?
Inactive.
RTB is inactive because now you look at the directions.
Yeah.
So it is like this, right? RTB, right? So yeah, so this is an inactive triple because T is not observed. So overall, this path becomes what? Is it active or inactive?
Inactive.
It's inactive. So information from L doesn't reach B. So yeah, so this is the answer for this is yes. Okay. So now what if you had T? If you observe T, what happens?
Uh, if you observe T, then
Let's write it here.
LRT will be active still.
Uh, so LRT will still be active. So the question is L, is it independent of B given T? Okay. So again, the paths are LRTB and we have LRT. So this is, you said LRT is still active.
Still active.
Yeah. And what about RTB?
RTB, I think uh, it should be. I'm not sure, ma'am.
Okay. So RTB is actually, it has the case three, right? So R, T, and B. And what happens is T is observed. So once you know something about T, information from R reaches T. Okay.
Okay, so it will be active.
Right? Yeah. So this is active. Okay. So yeah, this takes some time to, you're just seeing it now, all these cases. So it takes some bit of practice and to internalize these cases. Okay, so these two triples, all triples in this path are active. So this is the only path and this is active. Okay, so here what it means is that, this is not guaranteed. Okay, so this, it's no in general. The answer to this is no in general. Now, why? So, just a disclaimer: when I say in general, what it means is that there are examples. You can construct tables where there can be dependencies. Now, it can also be that the tables are constructed in such a way that this independency holds. So, there's nothing you can really say. That's why it's no in general. Okay, but only thing you can say when you say yes, it means that whatever be the tables that you put, that conditional independency will hold. Okay. All right, so we have this case. So what about, let's just do one more maybe. What about D and B? Is D conditionally independent of B given T? So maybe somebody else can attempt this. Maybe Tushar.
Yes, ma'am.
Yeah, you want to try this?
Sure,
Whether
ma'am.
whether D is conditionally independent of B given T.
Yes, ma'am.
Yeah.
So the paths are like DRTB,
Yes. So the path is just DR, TB. Yes. And
and triplets will be DRT and RTB.
yes, DRT and RTB. So what about DRT? It's active or inactive?
Here T is observed.
Yes.
Um, so ma'am, I think it will be active.
It's active, right?
Yes, ma'am.
Yes. So DRT, that's right. So DRT is active because D and T can be dependent. So there's, if you don't know R, so R is not observed here. So there's some dependency here that can arise between D and T. So it's an active triple. Now, what about RTB?
RTB. Uh,
T is observed.
yes, ma'am. Active. I think it will be active.
This is active. Yeah. So this
Yes,
is
ma'am.
actually the case 3 where, I mean, it's exactly this case here, right? You'll see something about T, and so R and B can become dependent. So it's the explaining away phenomenon. So again, so this path, I mean, so all the triples are active. So this path is also active. And so there is a way to get to B from D. So this, independence doesn't hold in general. Okay. Uh, yeah. So maybe okay. So I think I'm almost at the end of the time, but I just wanted to do like 2 more examples. Do you have something after this? Maybe I'll take about 5 to 10 minutes more. Is it okay? Okay, I assume it's okay since I don't hear any response. Yeah. All right. So now let's take a case where you have like multiple parts. Okay, so that is this example like this. You have R, T, P, and maybe something like this, some X here. Okay, so let's analyze between T and D. Okay, so there's no evidence. So are T and D, are they independent? So who wants to try this now? Maybe Meet, you want to try? Meet, you're there? Yeah, can you try this? T, whether T is conditionally independent, I mean, T is independent of T, so no evidence. So, what are all the paths? Can you tell me? Meet, is your mic not working or? Okay, my mic is not working. Okay, fine. So maybe somebody else whose mic is working. So Meet, I hope you're following through the classes. I mean, I hope the examples covered so far. I hope it's clear. Yes. Okay. So yeah, maybe can somebody else try? What is this here? Okay, maybe Satvik, would you like to try? Satvik, are you there? Okay. Okay, who is here? Who wants to try this? Can somebody
Yes, ma'am.
volunteer and try? Yes, Rishabh, tell. So
Yes,
this
ma'am.
is the network. You want to see if T is independent of D. So what are the paths first?
Ma'am, TXT or yes, ma'am.
So you have paths T, X, D. Okay.
Yes, ma'am. And we have the TRD also.
Yeah, so there are two paths. Okay. So is TXD active?
No, ma'am. TXT is not active.
Yeah, so this is inactive, right? You don't observe X, so this is inactive. What about TRD? So
Yes,
RTD.
ma'am. TRD is active, I think.
Yes, that's right. So TRD is active because R is unobserved, so
Yes,
information
ma'am.
from T can
T.
get to D.
Yes, ma'am.
Right? So here you have two parts. One is inactive, one is active. So there is a way to get from T to D via this path, TRD. So this independence doesn't hold in general. Okay. So that's how you, I just wanted to have this example where you have two parts. Okay, so now what if you observe R? So if T and D given R, if you observe R, what happens? So the paths are still the same, TXD and TRD.
Yes, ma'am. Ma'am, then TXT will remain as an inactive only.
Yes, right.
And as we know the
And
information of the R, so we can say that it is active only, TRD active only.
so you know R, so so it okay. So it comes like this, right? So for this part, it means that R is active. So what happens is once you know R, T and D become independent, right?
Oh, yes, ma'am.
So because of that, this triple
This is,
TRD is actually inactive. Okay, Rishabh, it's clear,
yes, ma'am.
right? So here you have two parts. Now both are inactive, so this is guaranteed to be true. Okay.
Yes,
Um,
ma'am.
this is clear. So I hope it's clear to all of you. Like, so this is how you would analyze if you have multiple parts. Okay, so one thing I want you to try this out as homework. So if you have both R and S, what happens? Okay, so this is a homework for you to try. Okay, uh, so again, you need to sorry R and X. Okay, not S. So this is R and X. See what happens here to both these parts. Now I just want to take one more example of one more network. So where you have like multiple parts. So let's take something like this: A, D, B, C, and this maybe. Okay, so this is the network. So I just want to do this so that we this completes the deseparation part, and we can move to the next topic from next week. Okay, so this is a network here. So now I want to analyze A and E. Are they conditionally independent? Are they independent without any evidence? So what are the paths? Maybe somebody can try. Noel, you're here.
Yes, ma'am.
Yeah. So can you try this between A and D? A
So
and E. Sorry. Yeah.
A B C D
So A, B, C, D, E. So this is one path.
A B D
A, B, D, E. Yes. Okay, so there are two parts. Fine. So let's analyze A, B, C, D, E. So what are the, what about A, B, C? Is it active?
uh,
Yeah. A, B, C.
yes, ma'am.
So A, B, C is active. right? So you can flow from A to C because you don't observe B. Now what about B, C, D?
It's also active.
B, C, D. So you don't observe C. Uh, okay. So what you need to consider for BCD is this network. Okay, so it comes under this case. Okay, because you're analyzing along this path A, B, C, D, E. So you don't actually look at this arrow here between B and D.
Okay,
Okay, so
so
this
it
is the
should be
case you need to
inactive.
see. So this is inactive, right? So there's no information of flow from B to D along this path, B, C, D. And yeah, C, D, E, what happens here?
It should be um, active.
This is active, right? Because you don't observe D, so information can pass between C and E. So this path is, you have these three triples. So is this path active or inactive?
It's inactive.
It's inactive. So the path is inactive. Okay, so this is an inactive path. So still you cannot guarantee this independence. Now there's one more path you have to check. So here, what are the, so the triples are A,
ABD,
yeah, and
BD.
BDE. Okay, so here what happens is ABD active.
Yes, ma'am.
Yes. And BDE.
Yes, ma'am. Active.
So this is also active. So, so that
Overall,
makes this path is overall it's active. Okay, so here one of the paths is active. So there's a way to get from A for information to pass from A to E. So this answer is no in general. Okay, so this independence doesn't hold. So let's just do one more and maybe we can stop after that. So let's just take A and E given B and C. Okay, so B and C are now observed. Sorry. Okay, so what this means is B and C are observed. So what happens here? The paths are still the same, right? So paths are still A, B, C, D, E and A, B, D, E. So now how does the analysis go?
the ABC will be inactive.
So ABC is inactive. Yeah. And what about BCD and CDE?
The BCD will be active.
BCD is active. Yeah. So again, the particular structure that comes here is this. So B is observed, C is observed. So this case is since C is observed, BCD is active. Now what about CDE?
It should be active.
Yeah, that's right. It's active because you don't see D, so CDE is active. So this path is active or
Overall, it's
inactive?
inactive.
It's inactive. So this is inactive. Now ABDE.
ABD is inactive.
So ABD is inactive. Correct.
BD is active.
Sorry. So ABD is inactive and BDE is
Active.
active. So overall, this path is also
Inactive.
inactive. Okay, so all paths are inactive. So this conditional independence holds. So you don't have a way to get from A to E. So they're separated out. So that's why this name D separation. So D, I don't know why D is there, but anyway, probably it's directed graphical models. I don't know why the D term comes, but the separation is just to see that there's no way to get from A to E. Okay, so try out some other examples that you can think of here. So for example, A conditionally independent of E just given B, whether it's true just given C, and maybe if you have just D, right? So some of these things, just try this out as homework to get some practice with this. Okay, so I hope this has been clear to you all. So I think now even your theory assignment 3, the last question gives you an example graph and to try out these D separation. Okay, so yeah, so I think I'll stop here for today, and we'll again continue on next week. So tomorrow we don't have class because of Diwali. We'll meet again on Tuesday. So thanks everyone. Wish you all a very happy Deepavali.
Happy Diwali, ma'am.
Thank you.
To you too, ma'am.
Happy Diwali, ma'am.
Thank
Happy
you.
Diwali, ma'am.
Thank you.